Like the hero, right? Okay, let's summarize again the process hypothesis. This is the time, and this is megawatts. So, we are all in phase. Okay. In the overall thermal balance, we don't make a difference between first basket and second basket. We just consider that for here this is melting, and here is refining. Okay? Here we have the charging first basket, charging second basket. Here we have tapping and turnaround. Turnaround, this is American denomination for furnace preparation, gunning, electrode slipping, etc. etc. Yeah? So that's why you see that the delay is charging the two baskets for the melting phase. Yeah? And a part of the delays, because we have delays everywhere. Yeah? Because the ladle doesn't come, the basket doesn't come, the crane is dead, or whatever. So we consider that 80% of the delays is during melting and 20% during refining. So, then, concerning the oxidization, we oxidize oxidization. No, this is E. During melting, we oxidize carbon and silicon. During refining, we oxidize as well carbon, first carbon, then iron and mangan. The air here is considered to participate to the oxidization. Here, no air. It's easy to understand. During melting, you have scrap here around, so the air getting inside the furnace is participating to the oxidization. Because the air meets the scrap. During refining, the air, of course, is getting in, but just meet the CO, which is coming from the bath and making a reaction here inside. There is no participation of the air to the thermal balance of the steel.
Yes.
Yeah? Except if you have too much air, and then you can cool down the bath. But this hypothesis I don't consider here in the thermal balance. I'm doing this not for diagnostic, to make a diagnostic of a furnace, but to design the best conditions for the furnace. Yeah? Okay?
So when we do not consider the air intake is, during the refining time, and it is
for the thermal balance,
not
for the off-gas. For the off-gas, it's considered to have the off-gas analysis and flow here. Yeah?
So if we sucked we just guessed from EAF, and if we take out so much the introduced gases from EAF, and then the atmosphere air coming. Yeah? No?
Yeah, no. Look, in the thermal balance, what we have seen, we just consider the condensed phases. Condensed phases, that means scrap, slag, steel. Yeah? The air has interference with the scrap during melting. So we can have a part of the air oxidizing the iron. That's why I have to consider it in the oxidization reaction and of course in the thermal balance. It's additional oxygen which is interfering with the overall thermal balance. During refining, there is no contact between the air and the condensed phases. There is just contact from the air together with the CO coming from the bath. Of course, it will be considered in the off-gas balance, but not for the thermal conditions of this. Okay?
Okay.
It's clear. If you have other ideas, you can develop, yeah? Because I mean, it took me some certain time to how to consider the air ingress, yeah? Because air ingress may have a lot of influence on the performance of the furnace.
I see.
Yeah. That means if you have excess air, in this case here, I have to try it whether it has
I'm in charge of the secondary methodology too. So I think the small items that we worry that air intake in the secondary methodology facilities, from the atmosphere. So I wonder the EAF is also considered the air intake from atmosphere. So you said during the refining times you think you don't need to consider the air intake.
For the equilibrium here.
I see. Yeah. Okay.
Yeah, because the air will not participate directly, this is my hypothesis, will not participate directly to the decarburization.
Okay.
Yeah. To a certain extent, it is wrong. Because if you increase the partial pressure of oxygen in the furnace atmosphere, of course it will contribute to the slag equilibrium.
Okay.
But for me, it's a very, very thin influence, which is not very important for the purpose of this kind of calculation.
Well, how about the stainless? In case of the stainless steel, in the stainless steel EAF has the bottom steering.
Not necessarily.
Not necessarily.
No.
Okay. No, I mean normally the EAF of the stainless steel, and they post plug, so 3 or 4 and so on. And when they do the bottom steering during the refining times, and then they can meet atmosphere air. So it is also that you do not consider, because it's a small items and it's not easy to adapt.
This is very special applications. And I just know Japan, who is using intense stirring for stainless steel.
In Europe is not
No.
used?
No.
Okay.
And neither in the US. I made myself, let's say, trials in stainless steel furnace with porous struts. And the result is that you increase the Cr2O3 of the slag.
Sure too.
You increase the chromium oxide in the slag.
Yeah.
And that's it.
Okay.
Especially during the flat bath. Yeah. Because you increase the contact between the steel and the atmosphere.
This is not useful.
Because there is no way to avoid to have, let's say, air in the furnace atmosphere. Otherwise it takes measures to tighten the furnace that you cannot work anymore. Yeah?
Okay.
And the best stainless steel furnace I know is the one who has no door,
Motor.
just a spout, and everything is going through a spout. And then you can reduce the air ingress by this way. And this is very important to get foaming slag, because if you have a door, then you cool down the slag, and it's much more difficult to make it react, because the slag is colder. That's why in certain plants, even they switch off the dusting for the refining phase.
Israel.
Yeah. I was astonished. I said, wow, what about the working conditions? It's going up, we have a good canopy hood, it's enough. Yeah, but then you breathe the CO2 you breathe the kind of dust. It's not good for the people. It may be good for the money of the shareholders, but not for the people. Okay.
Okay.
Then criteria here is 3 per ton of steel. For sure, let's say in reality you may have a different melting pattern. Yeah? For example, you reduce the voltage at the end of the melting phase of the basket number 1. Yeah? Here you have this kind of melting profile. Yeah? In fact, the megawatts you see in my model is that you get here an average megawatt. Yeah? Okay. Again, it's let's say we could implement this in the thermal model, but it's complicated unnecessarily the model. Yeah. For the furnace transformer, you just need to increase by 10% the capacity of the transformer, and that's it. Or 15%. Well, so maybe we can reconsider as well the carbon balance if you think it's necessary.
Yeah.
Yeah?
너무 잘 지금 야금 쪽에 그 이렇게 들어도 이해가 안 될 수도 있거든. 이렇게 어차피 이거는 수식을 놓고 자기 이해를 스스로 해야 되는 부분인데, 근데 이제 계속 듣다 보면 어느 정도 이렇게 뭐 수식 놓고 말고 크게 얘기할 때는 상당히 유용하게 될 거라고. 여기서 몇 번 듣고 이해하면 듣고 이제 나중에 수식 가지고 분석할 때 같이 좀 모르는 거는 서로 물어가면서 또 이제 박 박사나 그룹장님 계시잖아. 그러니까 이제 해서 좀 더 알아가면 될 것 같다고 생각합니다.
So on one side, I have oxygen from the lands times the efficiency, oxygen from the project and their efficiency, and here oxygen from air. Yeah. This is the total oxygen input of the furnace. And this is fixed for the furnace performance. Yeah. This is required for EAF productivity and kilowatt hour per ton. This fixed the amount of fossil energy I put in the furnace. On the other hand side, I have what I have available in scrap. This is scrap plus DRI plus hot metal, but generally scrap. Yeah? Generally speaking, scrap. Inside the scrap, we have carbon, silicon, mangan phosphorus to oxidize. This is given by the material balance. Okay? And then I have to inject carbon. This is given by the refining time and the flow rate I want to use in the furnace. And then comes here the calculated carbon. Charged carbon, which is to compensate the total amount of oxygen. Is it clear to you? Yeah. Yes. So easy, yeah? It was more complicated in the formula. Yeah? But this is just a translation of that. Yeah? Okay. You have the picture. Other questions? No. No? Perfect.
지금 기사 다른 이제
캐머라 엔진입니다. 캐머라 엔진.
메커니컬.
저렴하는 거 아니야? 카메라 감독님.
Well, so if we come back again, when you have a project, the first thing to know is to know the tap weight.
Yeah.
Yeah? So you fill the tap weight and the hot hill. For conventional furnace, hot hill is about 10%, yeah?
10%.
Yeah.
So some other companies said 15%. Too high?
15? Look, there were so many studies about how much hot hill do you have to keep in the furnace. What is sure is that the hot hill, if you increase the hot hill, you slow down the furnace. Yeah. The hot hill is necessary to have an aggressive power profile. Because if you don't have hot hill, for example, then you bore down and you expect, as the electrodes are in the scrap, roof is protected, you go full power. But then you go down to the bottom, and if there is no hot hill on the bottom, then you dig out the refractory. So the hot hill is there to maintain a certain, let's say, buffer to absorb the energy of the high power furnace. If you extend too much the hot hill, of course you extend the surface, so you increase the radiation of the hot hill during tapping, and then you have to put more energy to reheat the hot hill.
But as I heard, it's we increase the molten states, we can use the electric energy because a lot of the hot hills can help melting the scrap. And make only the bed. Yeah?
Hot hill is necessary, definitely, but too much. There is a critical size. For the DRI, if you go to, let's say, 90% DRI, you need to increase the hot hill. Because you have no time, not of, let's say, heat. Lot of liquid steel generated by the early melting when the electrodes are going down. This is something we will see with the ECS training, that the boring phase should be with the very low speed to enlarge the pit around the electrodes, and then you can create more liquid steel there.
아무튼 all over how many percentage of hotels when you're using DRI more than 90%?
Then I would
10%?
suggest 40%, yeah. 30 to 40%.
30 to 40%.
Yeah. Like when you have, let's say, a COS or a constil, then you need to go between 40 and 50%.
So there is some report said, I don't know exactly values, but it's ton, hot-till ton. Yeah, per hot-till ton, we can save electric energy. How much? Yeah, they say, but you said it is not big energy saving. Yeah?
No, I mean,
This
don't
is-
mix up, yeah. Having hot-till allows you to have, let's say, higher power input at the beginning of the melting phase. So you can go fast in megawatts, avoiding to have, let's say, refractory wear on the bottom. But too much, I don't see the necessity, because then you have more liquid steel to reheat. Except if you go to 40 or 50%, I mean the area of the hot-till doesn't change so much, yeah.
Or depths.
It's anyway the furnace diameter, yeah. So I mean you can increase there. There is no let's say disadvantage anymore.
Okay.
But between 10 and 15%, honestly, this is just theory, yeah, because ask the operators on the platform to maintain the hot-till at 10 or 15%. He doesn't care. He doesn't see any difference.
So as I saw the document and the technology trend in Asia, they want to develop using the more hot-till. I think it is one of the trend to develop in.
Maybe.
So Kiko.
But I've seen, increasing the hot-till, I mean, makes also another disadvantage because you need to maintain the bottom from time to time, once a day. Yeah? So then you have to drain the furnace completely, and then you have to rebuild the hot-till again. So it destroys a little bit the smoothness of the nail shop. Yeah? Or you have to, let's say, to have more management.
I think so.
Yeah, because you need to cut down the scrap on the previous heat, and even takes 2 heat to decrease the hot-till. It starts to be a nightmare. Yeah? Even for, let's say, a furnace having a low hot-till, I've seen sometime they need 2 ladders to empty the furnace. Yeah? They were expecting to have 10 tons and they had 40 tons, 50 tons.
Okay.
Yeah.
It is one of the main issue for the PINA project.
Yeah.
Is that the PINA project, they want to increase the hot-till to 40 ton.
Yeah.
Yeah, 40 ton. So they want to reduce the energy saving to escape the harmonics. Yeah. It's a more
hot-till, yeah.
Yeah, more hot-till means the reduce the harmonics. Yeah.
Yeah.
Flicker.
Yeah.
So they want to more the hot-till.
So they need to have a precise weighing system
Yeah.
for scrap and for ladders.
Yeah. So it is the client philosophy.
and yield management. But it's a long topic, it's not new. Yeah? It's already 30 years topic. How to manage the real weight of steel in the furnace. Even people try to put the complete furnace in the weighing cells, which is not working. Yeah. Because the complete furnace, you want to have a precision of, let's say, plus minus 2 tons on a big stuff which weighs 300 tons. Eh? How can?
And one more things why they encourage the hot-till. It means one is the slag. They do not want to the slags carry over to the ladder. It's a 5 kilogram per ton of the slag disposal is normal. But in in case of the BOF, there is a 2 ton or 3 ton, yeah, kilogram, 2 kilogram per ton, 3 kilogram per ton is normal. So
Because they have a stopper?
yeah. And so and no, that is a stop of the operators can do it in case of the postcode. They are very genius, and they cut the ladders, cut the slags, and they can make it. So they in case of the Vina project, they will have a similar line also, and it be cutted and slag is top of the water steel. Then we take to the EAF, but still the slag remaining in the top of the water steel. We can power out the water steels. Yeah, it's a proper size, and then we can take it back, and we cannot power the slag with the water steel, only water steel. That is one of the philosophy, I think.
Because Fuchs has it's a patented device to reduce the slag in the ladder, the carryover, to zero. To zero.
I also have idea.
Yeah. No, but it's working in Germany in one steel plant for special steel since now the 8 or 9 years. Already. Yeah.
Next time I want to meet. Okay. Keep going, please.
This is Buderus in Wetzlar.
That's right.
Okay, so then the mechanical will tell you the shell dimensions, and then depending on the furnace size, you know how many injectors you want to put. Yeah. In standard, for 150 tons we can put 5. For let's say 100 tons 4. Yeah. And here you don't need high power in case this was for DRI, so we don't need high power, but usually it's 3.5 megawatts. And per nozzle, it's not good to go higher than 2,500. Yeah? Otherwise, you have splashes and stuff like that. So minimum is 1,000 cubic meter per item, and maximum 2,500. Even 2,500 is quite high.
Oxygen?
For oxygen projects, yeah.
For the splashing.
Yeah. Then the carbon injection, you may have as many as you wish. And per length, the maximum is 30 kilograms per minute in case of, let's say, the modules, you know, like Danieli or whoever. Everybody is doing the same. You have the side lengths underneath the cojets. So the flow rate is limited to 30 kilograms per minute. But if you have door lengths, you may increase up to 100 kilograms per minute. Then oxygen length to the door. There is a lot of let's say different technology. I've even seen
door lengths,
yeah.
150 kilogram?
100.
No.
100.
Yeah.
No,
100.
Door lengths.
For door lengths, carbon door lengths, yeah, to have 100 kilograms per minute.
carbon,
When you plate up.
But the modern technology with the lens in the walls is much better because you can, let's say, divide it the carbon injection. When you have door lens, a lot of carbon is dislagged very, very quickly. Yeah?
But the other technologies, they put in the wall burners.
Yes,
The
exactly.
carbon injections
Yeah.
were in the wall,
Yeah.
and they the carbon lenses is assembled in the slag levels.
Yeah, they claim in the slide, but it's not really.
Slag level and
It's above the slag.
golden, bubble slags. And the first is melting time is low levels, and increased. They can the lenses between the slag, center of the slag, they charge the
Yeah.
carbon. It is one of the solutions.
Yeah, it's good. It's working well. The oxygen door lens, there are a lot of different possibilities. Even I've seen water-cooled lenses blowing up to 10,000 cubic meter per hour. So I don't see the interest of this used lens nowadays with the courgettes. So this is given by the customer.
Yes.
Slag basicity. You have this small comment. The slag basicity can be reduced if for carbon steel, I mean construction steel, yeah? Down to 1.6 if you are sure to tap below 1,600 and to have, let's say, saturation of magnesium from 8 to 10% of the slag. And if you want to increase the tapping temperature for special application, for example 1670, then you have to increase to 2.5. Yeah. And NGO minimum 5%. The saturation in this case is in the range of 11. So
how about this? It's normally the construction steels, it's lower than 1,600 degrees. Yeah? Carbon steel, the molten steel temperature for the carbon steel is
it depends on the
in case of the beam.
it depends. For example, with COS or consteel, you can tap at a low temperature, even 1580.
Yeah, 1580.
Because you have a lot of bath already, and there is no risk that there is unmolten scrap in the shell. For conventional furnaces, you are not sure about the homogeneity of the bath, so you have to increase a bit the temperature, because the temperature you measure in the door is not necessarily the same everywhere. And then afterward, it depends on how, let's say, the preheating of the ladle itself, yeah, and the distance between the furnace and ladle furnace. Okay, production time given by the customer. Scrap mix is given by the customer. And charging time, you have to be, let's say, in reasonable conditions. Yeah, 1 minute for basket charging is good performance. Usually nowadays we don't need to interrupt the process for temperature measurement. Tapping, again, it's average tapping. When the tap hole is new, then tapping time is longer than when the tap hole is closed, is old. Yeah. So here in this case, it's all the time the average tapping time. And tap hole refilling, etc. I mean, you have as well to have an impression of how the customer is working. Is it efficient? Then it's only 5 minutes. It can be only less than 5 minutes. If it's not efficient, it can be much longer. For example, Chagall, they have a turnaround time of 20 minutes, whatever they do. Then you fix the. I will put you again this macro for the megawatt calculation. Yeah, and then you put the process you want here. For the burner time, I mean, it's not necessary. This is the time where the injectors are used as burners. So it's not necessarily a long time, because then the efficiency is not of the burner is decreasing very quickly. So you can switch to the oxygen injection quite fast. And the door lens, I don't suggest to use it for melting phase, just for refining phase. And because it's better to keep the door closed as long as possible to avoid too much air ingress. So this fixes the process profile. Then you go to electrical power, you fill in the single line diagram, and then you adjust the MVA and the secondary voltage. You can adjust as well the current you need by this limitation here. This you don't need to touch. This you don't need to touch. This you don't need to touch, but the current we can adjust depending on what you need. Then you go to to analysis. You adapt the analysis of the fluxes whenever it's necessary. Eventually, you adapt the scrap analysis depending on the situation. You check the material balance. You adjust the iron content and the magnesia you need. And then thermal balance. You adjust the water delta T and off-gas temperature. You balance and you check here on this is the Sankey diagram. Yeah, where you have the liquid steel enthalpy, the energy of the slag. This is the energy absorbed by the water. I mean the water in the scrap. I mean I've put this here, but it could be included in the off-gas itself. Yeah. This is the water-cooled panels. So the slag usually is in the range of 60 to 80 kilowatt hours per ton.
Slag 60 to
80.
80.
Yeah, depending on the scrap cleanliness. Water-cooled panels, it's in a range of 35 to 40 for good furnaces. 35, 40. This is the water-cooled panels here. Off-gas is in a range of 120 to 150 kilowatt hours per ton, depending on how much fossil energy you put, because fossil energy will create a lot of CO. So if you have a lot of CO, you increase the off-gas energy. FEO, this is the eventually the reduction energy for the DRI. So it depends on the DRI. And this is the ohm losses. Electric is ohm losses, yeah? You remember the resistance in short circuit, time half current, square current, and so on. So this is the requirement of energy, this is the sources of energy. So liquid iron, if you put liquid iron, you will see that you have a figure here. I can put liquid iron. You see? This is the enthalpy of the liquid iron. Exothermic energy, it's coming from this value, approximately. This is the methane burned by the burners, and this is the electrical energy. I have not balanced here. What is So there is a small discrepancy because we need better balances. Okay. So this small table is giving you a diagnostic whether your thermal balance is okay or not. Yeah? Okay, now you have the process diagram. Usually I had a button here to select the parameter I want to display, and it was automatically done, but it's not working anymore since the 2007 version. They have changed totally the language there, and I didn't spend time enough to redo this stuff. But it's open, huh? So you can go and put additional parameters inside. It's not long. You put add here and then you select, but this is on the sheet. In fact, I have a hidden sheet with all the process schedule here. So if you want to add stuff like that, you can select here, knowing that the time. You see, the time is given by the column D. Column D is here. This is just time calculation. Well, you can select C or D. And then select this one here, and then whatever parameter you need here after. Copy and paste. Okay? What else do we have? We have another hidden sheet, which is the, let's say, the report. Yeah, this is for the salespeople. I have summarized the main items here. Yeah. Of course, this is not to give the customer, because the transformer is the result of my calculation, simplified calculation. This should be the base for the, let's say, transformer reactor design. What may be missing is the megawatts I need. And you don't need to display this, because it's coming automatically when you click here. Yeah, and you get a PDF immediately. So this is it for this model. I let you digest, and we go.
잠깐 또 잠시 들어주시죠. 그래서 잠시